You ever wonder how chemists know exactly how much of one thing to mix with another? It's not magic, and it's definitely not guesswork. It's a recipe, a fundamental set of rules that's running behind the scenes in everything from the medicine you take to the airbags that keep you safe. Today, we're cracking open the recipe book of chemistry itself, reaction stoichiometry.
Okay, let's dive into this. And I know what you're thinking. Pancakes? Really? But yeah, seriously. Mastering chemistry can start with something you do on a Sunday morning. Because the logic you use to make a perfect stack of pancakes, it's pretty much the exact same logic that powers incredibly complex chemical reactions.
So check out this recipe. The amounts are totally fixed. 1 egg gets you 8 pancakes. That's the deal. It's a non-negotiable ratio. So what if you've got a bunch of friends coming over and you need 24 pancakes? Well, you already know the answer, don't you? You're going to triple everything, which means you need exactly 3 eggs. See that? You just did stoichiometry and you didn't even break a sweat. All right, now let's take that same exact idea and swap our chef's hat for some lab goggles. Let's move from the kitchen into the lab. Because when you get right down to it, a balanced chemical equation is just a super precise recipe for chemists.
Look at this, side by side. On the left are pancakes. On the right, the chemical recipe for making ammonia, which is a huge deal for things like fertilizer. See how similar they are? Instead of ingredients like eggs and milk, we have reactants like nitrogen and hydrogen, and the equation tells us exactly how they have to combine. Just like 1 egg makes 8 pancakes, 1 molecule of nitrogen must react with 3 molecules of hydrogen to give you exactly 2 molecules of ammonia. It all comes down to these fixed, predictable ratios.
So this whole idea of using chemical recipes to do calculations, well, it has a formal name. And that name is the core of what we're talking about today.
And that word is stoichiometry. I know, it's a bit of a mouthful, but it's not as scary as it sounds. It actually comes from the Greek words for element and measure. So all it literally means is measuring the elements in a reaction. It's what lets us calculate the exact amounts we need to start with or the exact amounts we're going to end up with. No more guesswork, just pure, precise measurement.
So the big question is, how do we actually use the ratios from our chemical recipe? Well, for that, we have a simple but incredibly powerful tool. It's called the stoichiometric factor.
You see those numbers in front of each chemical, the coefficients? Those are our secret weapon. Now, in chemistry, we can't count individual molecules. They're just way too tiny. So we count them in big groups called moles. Just think of it like a dozen eggs. A mole is just a really, really big specific number of molecules. So from our ammonia equation, we can create these handy conversion factors. For every 3 moles of hydrogen we put in, we get 2 moles of ammonia out. And that ratio, written like a fraction, that's our stoichiometric factor. It's the exact same idea as our 1 egg per 8 pancakes ratio.
All right, enough theory. Let's put this into practice. Let's get our hands dirty and actually walk through a real calculation to see how this tool gives us concrete, useful answers.
Okay, here's our problem. We want to make 16 grams of magnesium hydroxide, the active ingredient in milk of magnesia. The question is, how many grams of one of our ingredients, sodium hydroxide, do we need to start with? And lucky for us, the chemical recipe we need is right there on the screen.
Now this might look a little complicated, but trust me, it's just a clear 3-step path. First, we have to convert the 16 grams into moles, because moles are the universal language of chemistry. Step 2, we use our awesome stoichiometric factor to convert from moles of what we have to moles of what we need. And finally, step 3, we convert those moles back into grams to get a number we can actually weigh out in the real world. This simple fraction you see here, this is the heart and soul of the entire calculation. We pull it directly from our balanced recipe. For every 1 mole of the product we want to make, our recipe says we must use 2 moles of our sodium hydroxide ingredient. This factor is the crucial bridge that connects what we know to what we're trying to figure out.
And after we run the numbers through those 3 steps, we get our answer. To produce 16 grams of milk of magnesia, we need to start with exactly 22 grams of sodium hydroxide. And that is the power of stoichiometry, turning a chemical recipe into a precise, practical number. But this isn't just about making antacids. Let's shift gears to a much more dramatic, high-stakes example to see why this kind of precision is so incredibly important. So imagine a car crash. In the milliseconds right after impact, a system has to make a life or death call. It needs to inflate a bag with gas, and it has to do it pretty much instantly.
The only way to make that happen is with a very, very carefully controlled chemical explosion.
This right here is the reaction that powers a lot of airbags. You have a solid called sodium azide that breaks down with unbelievable speed. We're talking hundredths of a second into sodium metal and, most importantly, a huge amount of nitrogen gas. That gas is what inflates
The airbag.
and this just shows you the magic of this reaction. Using stoichiometry, engineers calculate that a small mass, only about 100 grams of that solid chemical, can instantly generate around 50 liters of nitrogen gas. That's enough to fill the entire airbag and provide that life-saving cushion.
So, here's the crucial point. Get this recipe wrong, and it's a disaster. If you use too little sodium azide, the airbag won't inflate enough. If you use too much, it could inflate too aggressively and actually cause an injury. The amount has to be calculated perfectly, using stoichiometry to get the exact volume of gas needed. This is one calculation where there is absolutely zero room for error.
So there you have it. From a simple kitchen recipe to a life-saving safety device, stoichiometry is the invisible math that tells us how our world is put together. It's the language of chemical recipes, and it allows us to predict, control, and create. So the only question left is, what are we going to use it to calculate next?